All right, now we're recording. Okay, quick announcement. Something to today's stuff. You will not have class next Wednesday, March 30th. So I'll be away at a conference during that time. But it turns out, even with that, we're still able to cover everything that I plan to cover before the semester's over. So, all right. Now. Okay, so we're moving away from the wave equation a little bit, although today our focus will still be on hyperbolic PDEs, such as the wave equation. Now, you remember at the very, very, very beginning of the semester, I talked about for a general second order linear ODE, linear PDE, such as this one, that we had a way of classifying it. It was actually the first question on the test. But you examine the coefficients of the second partial derivatives, A, B, and C, and classify the PDE as hyperbolic, parabolic, or elliptic, depending on whether b squared minus 4ac, the discriminant, is positive, 0, or negative. And at the time, it seemed like a rather arbitrary classification. But what you'll see today is that there's an actual reason for it, you'll see the significance of the sign of b squared minus 4ac in terms of being able to, in terms of your approach to solving the PDE. So a PDE like this, in such a general form, is very difficult to solve. There really is no way to come up with any kind of a general solution formula for any PDE of this type. But what we can try to do is transform a PDE into hopefully a simpler one by making changes of independent variables. So instead of the independent variables x and y that we have here, we come up with new independent variables based on x and y, and then figure out what the PDE would be if the new variables. Perhaps we can make certain coefficients become 0. And maybe get a PDE in a much simpler form, and then try to solve that. In fact, that is what happened with the wave equation. We used a change of variable, like x plus or minus ct, and the wave equation reduced to a very simple PDE, u exceed eta equals 0, which is a problem that we knew how to solve from the very first lessons. So we'd like to do that in more generality. If we can maybe make some of these second partial derivatives terms 0, then we're that much closer to coming up with a solution formula, or at least understanding the behavior of solutions. So now we're going to see the real meaning of this system of classification. As I mentioned, like, maybe it can lead to a solution formula, or even if not, at least we can understand what sort of PDE we're dealing with, what kind of solutions we're dealing with. So suppose we have these new variables. So we're changing from x, y to c eta. Now at this point, we don't know how we want to relate x and y to c and eta. We're just going to make some change of variable, and the goal is to use the coefficients of the PDE to figure out what kind of change of variable is an advantageous one. So everything I'm going to show you, like we saw this a few lessons ago, I worked through something like this for a specific predefined change of variable to exceed eta. As I said earlier, x plus or minus ct. But what happens in the general case? So through heavy use of the chain rule, I can describe like du dx as du exceed dx plus du d eta d eta dx. Actually, I'm going to write this out a little differently so that you can more easily see where this comes from. So you're going to need a bunch of fractions like that. All right, so du dx, dx dx. X plus partial u, partial eta, partial eta, partial x. All right. So what we have here, this is an example of a multivariable chain rule. So one of these terms you would recognize as a single variable chain rule. And in multivariable calculus, you would have seen the multivariable version of this, where you have several terms of this type. Because notice the cancellation that you have. Du dx, dx dx. You cancel the dx's and you have du dx. Here again, you can cancel the partial with respect to eta, and you have du dx again. So that's how you can check to make sure that you have the correct derivatives being multiplied in your multivariable chain rule. So what we have is different terms, all of them canceling, if you will, and that's highly non-rigorous, and some of my colleagues might wince at that, but it really does help one understand all the possible combinations that lead to the derivative you're trying to express in the first place, partial of u with respect to x. So this is how you can relate partial of u with respect to x to a partial of u with respect to the new variables, xc and eta. So this is how we introduce them into the PDE. Then similar for partial of u with respect to y. We see you have the same kind of structure. Now we have a partial derivatives of the new variables xc and eta with respect to y. So now we have the first partial derivatives of u with respect to x and y expressed in terms of the new variables. And then we need to do the same with the second partial derivatives. So how do I do that? Well, if I take this, I'm taking derivative of ux with respect to x to get uxx. So now you can take a derivative of this with respect to x. And that's going to require the product rule. And that's what I use to get from here down to here. So here I have u dx with respect to x. And then c to x is as is. Then I go to uxc, stays as is, and I have xc xx. So a product rule applied to this term right here gives me these two terms right here. And then I do the same thing for this term. Product rule applied to this gives me these terms here. I'm not sure what's going on with the second line, which is exactly the same as the line above. So I'm going to comment that out. Okay. Actually, what I'll do instead, oh, never mind, sorry, they're not exactly the same. Sorry. Okay. Notice here I have u xc with respect to x. But I can change the order of partial differentiation. I can write this as ux with respect to xc. And the same thing over here, u eta x is written as now ux eta. And the reason for that is, I know what ux is because I've worked it out up here. So, again, so I'm going to include a new step here so you can more easily see what's going on. Okay. because now I can take ux here and ux here and replace them with this expression that was obtained earlier. All right, so ux is this. Here and here. Okay. So now ux has been substituted in. And now what I would do is take the derivative of all of this with respect to xc. So for instance, here I have uxc, differentiate with respect to xc, becomes uxc here. And then I have xcx and xcx, it gives me xcx squared. Similarly here I have unxc times xcx eta x, and that leads to one of these terms here. But I also get another one term like that from over here. So that's why I end up with two of these. And then this term was already here, this term was already here, so on. So then so that's how I get all of that in here. Now I have the second derivative with respect to x. Any questions about how we get from here to here, or any other part of this process for that matter? Uxy, uyy will have a similar form. You use the same kind of approach. Like I would take the derivative of this with respect to y to get this, and then the derivative of this with respect to y to get this. And you see that all these second partial derivatives have a similar form. But there's one thing I'm going to point out. Like, okay, when I'm taking a derivative of this with respect to xc, so you see I have xc down here, and I'm having cx times xcx and cx squared. But I'm using a product rule. I'm also going to have plus uxc, the derivative of xcx with respect to xc. So why doesn't that produce something? And I'll show you. If I have xcx with respect to xc, that would come from a product rule of working this out. Well, by changing the order of differentiation, that's the same as xc with respect to xc with respect to x. But derivative of xc with respect to itself is 1. So, and then take the derivative of that with respect to x and you get 0. So that's why you don't get anything from those terms. So now, all the derivatives that show up in the original PDE have now been expressed in the new variables. So then what I can do is I can replace all of those derivatives up in here, and then rearrange the terms according to partial derivatives of u with respect to the new variables. That way I can find out what the new coefficients are. The result is, here's my new PDE into new variables. So a bar, b bar, c bar are the coefficients of all these derivatives of u with respect to the new variables. And now I can show you the formulas for those new coefficients. And here we are. So you can see that they relate to the original coefficients and derivatives of the new variables with respect to the originals. So now we know that if we carry out some transformation of the original variables x and y to get new variables x, dx, what the new PDE will be. So that if we come up with a specific transformation of the change variable, we can see what the new coefficients are. But what we're going to do now is we're going to prescribe that certain new coefficients will be 0, and then see if there's a change of variable that will produce that outcome. So we would like A bar and C bar to be 0. So that way the only second partial derivative in the new equation will be this one, u with respect to c and eta. So that's the same second partial derivative term that we use to solve the wave equation. So that means what we're going to need to do is set both of these equal to 0 and see if some solution is possible. So if we can do that, the result will be a canonical, what's called a canonical form. So there's more than one possible canonical form. The one we're aiming for here is where we only have a term u with respect to c and eta. So I can start with this, and if I divide through by xcy squared, then I get this quadratic equation. And then similarly, I'll take this expression, set equal to 0, and divide through by eta with respect to y squared. Now I have really the same quadratic equation, same coefficients. Now, each one of these quadratic equations is going to have two solutions. So what I need to do is prescribe that cx over cy will be one of the solutions, eta x over eta y will be the other. So if we use a quadratic formula that gives us two solutions, we're going to prescribe that cx over cy is a solution where you choose a plus sign, eta x or eta y is the solution you get when you choose a minus sign. But that means that the only way that we're going to have two solutions is if b squared minus 4ac is positive. Or at least there's only going to get two real value solutions. And that is why that means that this kind of canonical form, where you end up with the only second partial derivative being with respect to c and eta, that can only happen if the PDE is hyperbolic. And so now we understand the significance of having a hyperbolic PDE, that this kind of change of variable that eliminates the a and c terms in the PDE is possible. Any questions up to this point? So we use these equations, xc is equal to an arbitrary constant, and eta equals to arbitrary constant. So you think of these as coordinate curves in the xc eta plane. Xc being constant, taking the derivative of both sides of this equation, lead to dxc equaling 0. But dxc would be equal to xx dx plus xcy dy by the chain rule again. And we have a similar result from the equation eta equals constant. So now we have these two equations, which if rearranged, gives us these two ODEs. And the only way that these ODEs will have distinct solutions, and therefore a viable change of variables from x and y to c and eta, is if the PDE is hyperbolic. So what we can then do is solve these PDEs. And then we'd like to see what the new coefficient b bar would be. Now, if I go back to the formula for b bar that we saw before, here it is. What I'm going to do is I'm going to factor out cy and eta y. And the reason why I'm going to do that is it will lead to cx over cy, or eta x over eta y, in what's left behind after you factor out. And that's convenient because I know what these are from these roots. So I factor out cy, eta y. And now I have cx over cy, eta x over eta y, which are equal to these roots. But notice here, cx over cy is one root, eta x over eta y is the other root. Here I have a product of the roots of a quadratic equation. And then here I have the sum of the roots of a quadratic equation. And it's good to know, in fact, it comes up in a number of situations. Anytime you have a quadratic equation, the sum of the roots is always equal to minus b over a. The product of the roots is always equal to c over a. So I can replace this part right here with minus b over a. No, c over a. I can replace this whole part with minus b over a. And that lets me simplify. So I've done that here. I've made those substitutions. And what do we get? If I factor out a 1 over a, or minus 1 over a, I get this b squared minus 4ac, which I already know is supposed to be positive. Otherwise, I couldn't be doing this in the first place. So that's my formula for the new coefficient, b bar, in the transform PDE. It's the discriminant, which we're assuming is positive in this case, times this scaling factor. And because of the change of variable I'm using, the coefficients a bar and c bar are already zero by construction. So now, this is my transform PDE because two of those terms have gone away. And the formulas for d bar, e bar, and f bar and g bar were given earlier. Actually, f and g don't change at all. And then here are coefficients for d bar and e bar. So a lot of the theory behind second order linear PDE makes an assumption that the PDE is some kind of canonical form. This is an example of such a canonical form where the only term involving a second partial derivative is this one. But at least if you know your PDE is hyperbolic, you know it's always possible to get it into this form. So then such theory can apply. Certain numerical methods for a solution also make the assumption that the PDE is in some kind of canonical form. So that's the importance of this classification and then transformation. It helps you understand your PDE and solutions. It helps you solve it too, whether it's analytically or numerically. Now, what I've shown you today, unfortunately, again, only applies in the hyperbolic case, where that quadratic equation has two distinct roots. If it's parabolic, you only have one root. So you can't transform x and y to two characteristic variables, you only have one. So you have a equal constant or c equals constant. The PDE is elliptic, so b squared minus 4ac is negative. You have complex roots. So, so for hyperbolic PDE, you can define characteristic curves, like c equals constant or a equals constant. You can have both. Here you only have one. In parabolic case, elliptic case, you have none. So all of those affect what kind of canonical form you can transform a PDE into, and how you go about solving it once you do. But here, and also for cases, for sake of homework, we're just going to concern ourselves with the hyperbolic case. Actually, one thing I want to check. Because on one occasion I taught the other PDE class that we have, which is Math 606, so this is for graduate. The Carl spending time on classification there too. Okay. I'm checking to see if I have something that I can show you. Okay. I need to unshare and reshare real quick. All right. Don't want to end the meeting, I just want to stop sharing for a second. All right. Okay, so this is from my notes from Math 606, and I'll return to our notes a little bit. So this is the simplest possible canonical form where you don't have first derivative terms, yet where this is the only term with a second partial derivative. So that's what we're dealing with now. And you saw this when deriving the Lemberg solution from a wave equation. If your equation is not hyperbolic, what canonical form can you aim for in that case? Well, for example, if it's parabolic, this is a canonical form that you can aim for, where so A bar is non-zero, but it's possible to make B bar and C bar equal to 0, and then this is a first-order differential operator, meaning that it consists of first partial derivatives of u with respect to either of your variables, but not second partial. And then finally, for the elliptic case, this is your canonical form. So your A bar and C bar would be non-zero, but B bar would turn out to be 0. Okay. So, and then, so suppose it worked out in these notes. So I'm just bringing this up for sake of completeness. This is essentially Laplace's equation with some lower order terms. Whereas in the parabolic case, the heat equation is an example of a parabolic equation. Ut is equal to uxx. So then we have this term corresponding to uxx, or uxxe, and then you have some first derivative term in here that accounts for the ut part. So depending on whether b squared minus 4ac is positive, 0, or negative, that determines which canonical form is possible. All right, so now I'm going to show you an example of this process I showed you carried out for a specific PDE. So we have y squared uxx minus x squared uyy is 0. So here are coefficients a, b, and c. So b squared minus 4ac would turn out to be 4x squared y squared, which is positive. So unless x and y are 0, the equation is hyperbolic. So here we have, coming from our quadratic equation that defines xex over xey and eta x over eta. What was that? Okay. And so here I fill in A, B, and C in here and simplify as much as I can, and I get x over y and minus x over y. Now at this point, I still don't know what a change of variable like C and eta will be, but I'm starting down the path of figuring them out. And these equations are my starting point. So now, this is what we have in general. dy dx is equal to minus xex over xey. And so that's what I have. In this case, I have minus x over y. And I also have, in general, dy dx is minus eta x over eta y. In this case, that will give me x over y. So in fact, if you're given a specific PDE and you establish that it's hyperbolic, then you can actually jump. You work out what these formulas are first, xex over xey, eta x over eta y, and then you can jump directly to having these ODEs, where it is dy dx is equal to the negatives of these expressions that you get here from your A, B, and C. And then you just go about solving these ODEs. In this case, the ODEs are separable, so they're among the nicer kinds to solve. So rearranging them, you get these two. And then you can integrate both sides. Left side with respect to y, right side with respect to x. Now, when you integrate, for example, this one, you have 1/2 y squared plus 1/2 x squared is equal to a constant, because you're going to have a constant of integration. So for this equation, your constant of integration you'll call that xc, because you're starting from xc equals constant. Here, you're going to have a constant of integration as well. That constant of integration is eta. So that's why this equation, this ODE, leads to this formula for xc, and this one, when you solve it, leads to this formula for eta. So the constants of integration lead to xc and eta appearing in these formulas. So now you have formulas for the new variables xc and eta that come from these ODEs. Or questions about how that was arrived at? So now, when I know what xc and eta are, and I can take their derivatives with respect to x and y, I can fill all that in here. Well, I know that a bar and c bar is 0 because that's an artifact of this whole procedure. And here's my formula for b bar. So I just fill in all the partial derivatives of xc and eta with respect to x and y that I need. And thankfully everything simplifies drastically, and I have this. And then I can also work out d bar, e bar, all of these. So make sure to work all about it. You can't make assumptions as to which ones will be 0, except for f and g, because f and g do not change, because they don't involve any derivatives of u. So this is the new PDE that comes out of this. So we only have this one term with a second partial derivative. Everything else involves just first derivatives. But we're not entirely done, because we like to have the PDE in terms of only one set of variables at a time. But here we have x and y and c and eta all in here. We like to have everything in terms of xc and eta only. Now, y squared plus x squared, that was xc. So I can replace that in here. Y squared minus x squared, that turns out to be eta. So I fill that in here. And then, so it turns out that eta squared minus 6c squared works out to be minus 4x squared y squared. So that allows me to substitute, to replace this x squared y squared with this. So this term, this coefficient expressed in terms of c and eta becomes this. So now, this is my transform PDE in terms of entirely the new variables. So questions about how this unfolded? So this is an example of a problem from this lesson where you're given a specific PDE and you figure out what the new variables c and eta are in terms of x and y, and then figure out what the PDE will be in the new variables. And assuming the PDE is hyperbolic, the only second partial derivative term you should get is this one, with some coefficient here. Now, another canonical form, if you've already gone to this, this canonical form, you can make a third change of variable. So the new variables now are, the new variables are alpha and beta equal to xc plus or minus eta. So you can work out the partial derivatives like before. And notice that the only second partial derivative term you had before, u xc eta, now becomes this, the new variables. Which actually makes sense because we know the importance of this kind of term in solving the wave equation. But you think of alpha as x and beta as t, this is like uxx minus utt. Well, that's the simplest form of the wave equation. Utt is equal to uxx. So you can recognize from things we've seen before that both of these are forms of the wave equation. So then this is the canonical form that you get, in this case, in terms of the coefficients okay, so if you made the first change of variable to get to here, then the new coefficients from this alternative canonical form are given here. So the coefficient of your second partial derivative terms does not change. And then you can take simple combinations of d bar, e bar to get the coefficients of your first partial derivative terms here and here. And then the f and g once again don't change. So because some theory behind a wave equation assumes the PDE is in this form, so this alternative canonical form for hyperbolic problems can be useful. So this is how we can obtain various canonical forms for hyperbolic, for second order linear PDE that are classified as hyperbolic. Do we have any questions about this or about homework problems? Yes.
Number 7, lesson 20.
Okay. Lesson 20. Okay. Okay, I don't know how far you've gotten with this. Or
I wasn't sure if we were supposed to solve it, like completely solve it, or supposed to just write like we were supposed to use the eigenfunction extension of k of x. I didn't really get too far into it.
Okay. I guess there's room for interpretation with this problem, and that's because I think it's telling that they did not say solve the non-homogeneous PDE, especially since you're not given specific initial data. Okay. Here's what I would consider an acceptable answer for this. Because when you're solving a non-homogeneous PDE, just like with the heat equation, you can express the solution as a sum. I'm going to write this into the notes. Okay. All right. So the assumed solution has an eigenfunction expansion u of xt is equal to a sum right, xn of x, tn of t. So this form, we saw this form from a heat equation that was non-homogeneous, and that would hold true here as well. Where the xn, x are the eigenfunctions from the homogeneous spatial ODE, and T are time-dependent coefficients. So, see what the information they give you here. Okay. So, I'm fine with answering these two questions. Since you're given specific boundary conditions, at least, what are these? And the second is, what is the initial value problem? That's fine. So there's an ODE question, and what about initial conditions? And you wouldn't be, I mean, you can express the solution to a point, but let's see. Yeah, certainly you can't get the coefficients of this. Okay. All right, so if you take that far, because then if you were given more specifics, then I would know that you would be able to complete the solution process from there. And because it's a wave equation, unlike the heat equation, your ODE is second order. So that will give you an idea of what kind of solution you can expect when you solve problems like that in like the Math 285. Are there any other homework questions?